Td0 methods. So these methods that we will be learning are for online learning. So it's not like you have to iterate over all possible states and all possible actions as in value iteration or policy iteration that we have seen. Here you can actually deploy the learning algorithm, the reinforcement learning algorithm, inside a working agent. So we have to get to the episodic setting. So this is one episode of Pac-Man. The yellow semicircle is Pac-Man, and as soon as it gobbles everything, the episode is over. So this is another episode. And so it continues. And Pac-Man, this, what you're seeing here is actually based on reinforcement learning. And Pac-Man is learning to play. And once the game is over, a new episode begins. So we start with the episodic setting. The Sarsa sequence is given by ST, AT, RT, next state ST plus 1, and next action AT plus 1 until infinity. The reward sequence is RT, RT plus 1, RT plus 2, RT plus 3, and so on. And we are at time t. So the discounted total future reward starting from time t is uppercase RT, which is equal to immediate reward, lowercase rt, plus discounted future rewards. And we saw that the further away we go into the future, we discount more and more because of the uncertainty. So this is the expression for uppercase RT. And from that, we can get the recurrence relationship. RT is equal to lowercase rt plus gamma times uppercase RT plus 1. Now, what's the value function? By definition, the value function is equal to the expected RT, because RT is stochastic, the transitions are stochastic. That's why we need the expected value here. So expected total reward is equal to the value of the state, which is equal to lowercase rt immediate reward, which is deterministic, plus gamma times expected reward at t plus 1. And we can expand that further, so which is equal to RT plus gamma RT plus 1 plus gamma squared times expected total future reward starting from t plus 2 and so on. So we begin with Td0 method. So VTS is equal to RT plus gamma expected value of RT plus 1. That's our starting point. Now, what do we do in value iteration? VT new is equal to reward plus gamma times RT plus 1. That's what we would have done if we were running value iteration. This is simply Bellman's equation in episodic setting. But value iteration is not for online learning. So let's define the difference. We had the old value, V old, and we have the new value, V new, and V new is equal to this expression here. So let the difference be denoted as AT. So AT is equal to V new minus V old, which is equal to, since we know the value of V new, so this AT is equal to RT plus gamma times expected RT plus 1 minus VT old. Whence VT new is equal to VT old plus AT by definition of AT. AT is the amount of increment on the value that you do to get the new value. So VT new is VT old plus AT. So this is our increment. Instead of doing the full increment as in value iteration, what we will do now is only a fraction of the increment will be applied. So instead of adding all of AT to get the V new, we will get the V new by adding to V old a small fraction alpha t of the actual increment that we should have applied. And why do we do it this way? Because, well, this is not the, this VT new is only based on one transition from t to t plus 1. And each time you implement the action, you'll get a different reward or line up in a different state and so on. And so this is uncertain. And because of the probabilistic nature of the transitions, and therefore we should be very careful in applying the increment. So instead of applying the full increment, we apply a small amount of increment to the value. And this alpha t is between 0 and 1. So alpha t should be quite close to 0. It should be small, so that we apply cautious increment, so that if we apply the same increment over and over and over again, then we will actually converge to the real Vs. Okay, so this means that Vt new is Vt old plus alpha t times this quantity within parentheses, which is equal to, now I simplify this further, this is alpha t, this epsilon is alpha t, that's a typo, and Vt 1 minus alpha t times Vt old plus alpha t times Rt plus gamma expected value of Rt plus 1. Td0 method. So we just saw this update rule for Vt new using Vt old, and the expression here includes the expected value of Rt plus 1. And we also know, keep this in mind, that the expected value of Rt plus 1 is Vt, V, the value. Okay, so now how do we, within this episodic setting, use this experience, St, At, Rt, St plus 1. So this is one step, and we're not using At plus 1 at this stage. So it's not Sarsa, it's just Sars. And using this experience, how do we update our Vt new of our current state St? This question is using something very similar to this expression here. So this is how we update. Vt new of St is 1 minus alpha t of the old value of the same state, Vt old of St, plus alpha t times Rt plus gamma times, now instead of the expected value of the future total reward, I have replaced that with the old value of the state st plus 1. And this is Vt st plus 1 is, of course, the by definition, the expected value of Rt plus 1. And this quantity within parentheses is called temporal delay target. And that's why the name Td. Now, the alpha t's must satisfy the Glee conditions. And what are the Glee conditions? First of all, it should be decreasing with time t, and summation alpha t should be equal to infinity. But summation alpha t squared should be less than infinity. So these are the Glee conditions. So for the value function, when the agent gains experience from a state st, it takes action at and gets a reward rt and transitions to state st plus 1, then we just saw that this is how we would update the value of the state st. So Vt new st is given by the expression, and it uses Vt old st. And it also uses Vt old st plus 1, this one, because this is the expected value of the total reward Rt plus 1. Now let's see how we can write down equivalent expression for the Q value function. Now for the Q value function, we actually need At plus 1 here. So our experience will be st, at, rt, and then the next state st plus 1, and the next action at plus 1. And why? Because this is the equivalent expression. So qt new of st at now, because we took action at, is 1 minus alpha t times the old value, just like here, plus alpha times the reward plus gamma times. Now here I had Vt old. I didn't have any action specified here, but now the action needs to be specified. So it's Rt plus gamma times Qt old St plus 1 At plus 1. At plus 1 is the action taken at time t plus 1. So you need to remember that the action needs to be known one step ahead of time when updating Qt. Now, why at all do we need a stochastic policy? This gives you an answer. This is a two-armed bandit, which is a slot machine in Vegas, except that it has two levers, two arms. And when you press lever 1, the average payoff is mu1, and it has a standard deviation of sigma. And when you press lever 2 instead, the average payoff is mu2 with a standard deviation again of sigma. Now, it's obviously a good idea to use the lever which has the higher payoff. If mu1 is higher than mu2, then you always keep pressing lever 1, otherwise you keep pressing lever 2. And you have a total of 100 trials. The problem is mu1 and mu2 are unknown to you. So what is to be done? So here we have the problem of exploration versus exploitation. What is exploration? Exploration is, since you don't know mu1 and mu2 which is more, you pick an action at random. Lever 1 is one action, lever 2 is the other action. These are the two actions. And so you are searching. Exploitation is when you pick the lever which has the higher average pay of mu hat. So you don't know mu1 and mu2, but each time you keep track of the rewards that you are getting by pressing lever 1 and lever 2 respectively. And then you average them out, and that gives you an estimate of the payoffs, mu. And that's mu hat. And remember, mu hat could be quite different from mu if sigma is high. And just because mu1 could be more than mu2 doesn't mean that mu1 hat could be more than mu2 hat. You could be wrong. So the more number of times you collect samples, the more number of times you hit both levers, the better will be the estimation mu hat of mu. So now suppose we have too much exploration. We randomly pick too many times. Then what happens? We simply run out of trials. We have a total of 100 trials. At the end, we'll end up with very good estimates of mu1 and mu2. And at the end of the 100 trials, we'll know which one is a better lever to press, which one has a higher payoff. But unfortunately, we'd have run out of trials. What if we exploit too much? Well, in that case, what if the estimates are wrong? If we don't explore too much, we explore too little and start exploiting too much with only few random actions, then what happens is our estimates could be wrong, and we would then be using the lever based on a false estimate. So the correct approach is to strike the right balance between exploration and exploitation. And initially you use more exploration, and as the estimates become better and better from the number of samples, then you gradually begin to use more exploitation. So let's look at a few available stochastic policies. Greedy action. If you have the Q values and then you take from the state A, you pick the action which has the highest, the maximum Q value, that's the greedy action. A is argmax QSA prime. Now, epsilon greedy policy is one of the well-known stochastic policies. We draw at random a number R which is uniformly distributed in the interval 0 to 1. So it's a random number uniformly between 0 and 1. And if R is less than epsilon, where epsilon is a predefined number, constant, then we pick a greedy action. Otherwise, we pick a random action. So with the probability of epsilon, we are picking a greedy action, and with the probability of 1 minus epsilon, we are picking any random action from the set of all actions. That's the epsilon greedy policy. Another good example of a stochastic policy is the softmax policy. So it uses the softmax function, which is as follows. So probability of picking action A when in state S is directly proportional to e to the power of the Q value, QSA. So it greatly exaggerates better Qs, better actions because of the exponentiation. And since we need to normalize, the probabilities should add up to 1. So the probability of taking action A from state A is equal to, the numerator is e to the power of QSA, and the denominator is the same e to the power of QSA, and now A prime summed over all possible actions, A prime. A variation of the softmax policy is called the Boltzmann policy. The Boltzmann policy includes a new parameter called T, the temperature. And when the temperature is infinity, when the temperature is very high, what happens is e to the power of q divided by infinity is e to the power of 0, which is 1. And so the numerator is 1, the denominator is equal to 1 for each term in the summation. 1 over the number of possible actions is the ratio. And so all actions are equally likely to be picked when t approaches infinity. So it's a random policy. At the other extreme, when t approaches 0, when t is really small, this probability becomes 1 for the optimal action and becomes 0 for all the other actions. And so when t approaches 0, the Boltzmann policy is more like a greedy policy. And the trick is to gradually lower t as the training progresses. You start from a very high value of t, and then as the temperature, as the training progresses, when the Qs have accrued some values which is non-zero, then you start cooling, and you cool gradually. So the policy transforms from a purely greedy policy, for a purely random policy initially, to gradually it becomes greedier and greedier, and at the end it becomes a very greedy policy. Now let's begin with our first algorithm, online algorithm. And this online algorithm, the first one will be for policy evaluation, and it will use the values, not the Q values, just the state values, V's. So our experience, each time we collect an experience like this, ST, AT, RT, ST plus 1, then we update the value of state ST according to this expression. So VST, this is the new value of VST, this is the old value of VST. And what's this? How is the new value of ST given by? 1 minus alpha t of the old value of V plus alpha t times what it should be, RT plus gamma V of ST plus 1. And so now let's the algorithm. Online policy evaluation. So at first we initialize all state Vs to 0 or very small random values. So all of these are initialized. And then you see a repeat end loop. This is repeat forever. That's because it's online, so you can keep learning forever, lifelong learning. And so if you're training a robot, the robot can always perpetually be training itself. Maybe with smaller and smaller increments, because alpha t might keep decreasing towards almost 0 when t is very high. But nevertheless, it can, in theory, keep learning. So repeat forever, and within this repeat loop, we will have one episode each. So an episode will be buried within this repeat forever outer loop. So we initialize t equals 0 and the initial state st s0 to be the initial state. Each time we begin an episode, this is what we do. And then we begin running the agent, which could be a robot or whatever, for that particular episode. And since it's episodic, again, while not terminated, it's not like a fixed number of iterations. So while not terminated, while the goal state is not reached or something, what we do, we pick an action, AT, based on the policy. This is policy evaluation. So the policy should be known. Action, we pick action AT, and then we implement action AT upon the environment. And because of this action AT, the environment transitions from current state ST to state ST plus 1. And we get from the environment the reward RT. This is the instantaneous or immediate reward. We also get the next state ST plus 1 that the environment is transitioning to. And here's how we update. V of ST is 1 minus alpha t V of ST plus alpha t RT plus gamma VST plus 1. This is the usual update rule, and then we increment t, the time step. So this is online policy evaluation. Sarsa 0. This is the same algorithm for policy evaluation. However, instead of V's, we shall use the state action values, the Q values. And the experience now is ST, AT, RT, ST plus 1, AT plus 1, because when we are using the Q's, we need a second argument. That's why we need AT plus 1 also. So our update rule is old value QSTAT is updated with 1 minus alpha t of QSTAT. This is the old value, excuse me, I misspoke. This is the new value. So the new value is equal to 1 minus alpha t of the old value plus alpha t times the current reward signal plus discounted times QST plus 1, AT plus 1, where AT plus 1 is the next action. And this is Sarsa 0. This is the Q value equivalent for policy evaluation. And we see the initialization Q's to very small or 0 values are right at the beginning. And then we see the repeat forever loop as before. And we are now at the initialization step. So we initialize t to 0. Each time we start a new episode, t is initialized to 0 and st is the initial state. But since now we are dealing with the Q values, we also need the action a priori. So AT is the initial action based on policy. So we have to find out AT before we begin the while loop. So now we run the episode. So this is all we have done for initialization, and now running the episode. So we implement action AT, which has already been identified here. We have already obtained AT. So we implement it upon the environment, and then the environment transitions to ST plus 1. It returns the reward RT and the next state ST plus 1 to the agent. And then AT plus 1 is the next action based on the policy that we again need before Q learning step. So now we are using this AT plus 1 also for Q learning. And this is the usual update rule. And then we increment T to T plus 1. So this is Sarsa 0. Why the 0 here, you'll understand in the next set of slides. Q learning, or rather Q0 learning, this is the equivalent algorithm for policy improvement. So we initialize the Qs, and then we have the usual repeat forever, and we initialize T and the ST. Now here, since this is for policy improvement, we will take the argmax of 8 actions. So we don't need actions a priori. as much as before. So while not terminated, so this is when we run each episode, and so we find the greedy action AT, the optimal action, which gives the highest Q, and then we implement that action AT upon the environment, and then the environment transitions from ST based on action AT to state ST plus 1, and we get the reward RT and the next state ST plus 1 from the environment, and then the update rule. We don't need AT plus 1 here because we are doing the argmax. Why? Because this is policy improvement. And so this is the update rule for policy improvement, and then T is incremented to T plus 1. So this is Q learning. And a good way to do problems is to use Q values that have been obtained from Sarsa before we do the Q learning. Otherwise, it's the exploration exploitation issue. Q learning is purely exploitative. It's only picking the action that's found to be the best. And if you don't have enough samples of all actions, you don't know which action is actually the best. So you need to try from each state ST, you need to try all possible actions enough number of times before the estimates of Qs are good enough. Therefore, it's a good idea to start with Sarsa and then use Q learning. Unless you are using Boltzmann policies for Sarsa, in which case Sarsa automatically gradually transforms to Q learning. Now here's a comparison of Q learning and Sarsa for a very simple 2D grid problem. In the left we have Q learning, and the Q learning learns the optimal path. Of course, it has to do some initial search, so you have to apply Sarsa initially before you do the Q learning. And if you keep applying Sarsa, then the path taken is more safe because of the random actions involved in Sarsa. What happens is occasionally one could get trapped in the forbidden states here. You see these are forbidden cells, and so to avoid the forbidden state, it takes a longer trajectory to reach the goal, the end.